Hello everyone, welcome to this meeting. This should be the second session for our topic, which is dependence of random variables and conditional distributions. And that's a part of this half-a-year series of statistics lectures, statistics meetings. If you are connecting for the first time, or if you see this video for the first time on YouTube, then let me say that there's this sign-up form. So please fill out the sign-up form, then you will be able to see the different resources that we have for these different classes. And yeah, so this is session 2 of dependence of random variables. The last time I spent time talking about expectations and definitions of expectations of random variables. It was a relatively long and technical discussion. But here I would just like to remind you of what we did. So we built this general definition of expectations in 4 steps. First, we defined expectations for indicator variables. Yeah, what were indicator variables? It was just the 0, 1 variables that would be equal to 1 if some event happens. They would be equal to 0 if that event does not happen. So the definition there was easy. The expected value of that indicator random variable was just the probability of the event. Then we generalized this to so-called simple random variables. These were finite linear combinations of indicator variables. And the definition there was basically this one. We would say that the expectation is the appropriate linear combination of these different probabilities of the different events corresponding to the different indicator variables. So this was still relatively straightforward. Then we had a little bit more complicated argument, which was generalizing the concept of expectations to non-negative random variables. And we said that the expectation of some non-negative random variable x would be the supremum of expectations of simple random variables, such that these simple random variables are always smaller or equal to this random variable x. And yeah, the supremum is taken over all of the possible simple random variables that satisfy this condition. So this was a third step, and in the fourth step, we basically generalized this to arbitrary random variables, and that was by splitting some arbitrary random variable x into a positive part, that was this x plus, and the negative part, that was this minus x minus, and both x plus and x minus were actually non-negative random variables. And for that reason, we already had expectations defined for them. And eventually, the expected value of x was the difference of the expectation of x plus and the expectation of x minus. So this was the main content of the meeting the last time. Something a little bit technical, but crucial. We definitely would like to apply expectations to all kinds of random variables, not just discrete random variables, not just continuous random variables. So at this moment, I would like to ask if people have questions about the content that we had the last time. I would be happy to clarify if something was unclear there. And yeah, if we don't have questions about that, then let me also mention here that we also discussed the concept of measures. And it's something that I will not be using today. Today I will be focusing on relatively simple things. So I may want to provide some reminder of measures the next time. And yeah, definitely today we should be focusing on issues related to the dependence of random variables. Today I would like to talk mainly about things that have to do with discrete random variables. It's because things are substantially simpler if you assume that your random variables are discrete. And then The next time we should discuss different complications that are going to arise if we allow our random variables to be continuous. In fact, there's a paradox, kind of an interesting paradox that we should discuss the next time. Something that people don't quite appreciate. Often people start thinking about the dependence of random variables in this kind of context of discrete random variables. And then they don't get the concepts right in the case of continuous distributions. So I would definitely want to make sure that people understand the subtleties in there. And yeah, let me also say that the subtleties have to do with the exact type of conditioning that you would do in the case of continuous variables. So the next time it will be kind of more technical and maybe also more surprising. There will be some paradox involved. Today, it should be relatively straightforward. Probably many of you have already been thinking about related issues. So yeah, you can think of it as some kind of recapitulation, but hopefully I will also provide some more intuition that maybe you have not had, even when it comes to the dependence between discrete random variables. So that's the plan. Today, it should be mathematically relatively straightforward. The next time, let's focus on interesting subtleties. And yeah, do people have questions at this moment? It could be about the content that we had the last time. It could be about anything else. Okay, if we don't have questions, then let's jump in. Let's talk about distributions of random variables. So first, I would like to introduce properly the concept of joint distributions. This will not be really focusing just on discrete random variables. So this will be a general definition that we will use both today and the next time. But the rest of the discussion today will be focusing on discrete random variables. And yeah, previously we talked about random variables just one at a time. This time we would like to think about several at once. So let's say that we have capital K random variables and we form some vector x. So this vector x is going to contain these individual random variables x1, x2, x3, and so on, up to xk. And what I mean by this notation, I simply mean that if you have this vector x and you take its value for a particular outcome omega, then it's going to be a vector that consists of the functional values of these individual random variables. So random variable x1, x2, up to xk, all evaluated at this outcome omega. Yeah, I don't know if I should provide here a quick example, but yeah, if you think about omega as representing the state of the atmosphere everywhere in the world, for example, at a particular time, then these different random variables that you may be interested in could be, say, the temperature in Tokyo, temperature in Kyoto, and so on and so on. And you may want to form a vector of these and talk about how they depend on each other. So if we want to talk about the distribution of this vector x, or like some collection of random variables, we need to use this following definition here. We will talk about the joint distribution px, so it's going to be denoted px. It's going to be a joint distribution of this vector x, which means joint distribution of these individual components, x1 up to xk. And then we will say that the value of that distribution evaluated for a particular set B, or you can say region B, that's going to be the probability assigned to the set of possible outcomes such that x belongs to B. This is actually analogous to what we had before for individual random variables. If someone asks you what is the probability that X belongs to some set capital B, then you would look up all of the possible omegas such that the value of this random variable X belongs to this set B, and you would find its probability measure. So this capital P, that was the probability measure associated with our sample space and with these individual outcomes. And we are going to use this probability measure to also define the probability of this region B, or capital X belonging to this region B. So I think I will have to say more about the technicalities, but before that, let me check the chat. Can we think of omega as a sample space? Right, yeah, so this little omega, these are going to be the individual elements of the sample space. You will have some large sample space, capital omega, and these little omegas, they are individual points, individual elements of that sample space. And a question, what is set capital B in your atmosphere example? For example, it could be specification that the average temperature of Tokyo, Kyoto, and Osaka is between 20 degrees and 21 degrees Celsius. That is, we are going to specify some kind of restriction on the values of these individual components of capital X, and that will define our set B. Which restrictions you choose, that's up to you. It doesn't have to be one restriction, can be more restrictions, and so on. But it will be simply some kind of range of allowed values of this particular vector that you want to think about. And it doesn't have to be average temperature. Maybe you want to specify that, say, maybe the temperature in Tokyo is between 20 and 21 Celsius, and the temperature in Kyoto is between 20 and 21 Celsius, and so on and so on. So some region to which capital X should belong. Technicalities. So one thing that I definitely should mention here is that this capital B is going to be some subset of r to the power of k. So r here means all real numbers. The power of k indicates that we will have some high-dimensional space of real numbers. So specifically, we will have k-dimensional space. And then if you have this k-dimensional space, you can think about the Borel sigma field associated with this k-dimensional space. We didn't talk about it much explicitly. We mainly talked about the Borel sigma field in the one-dimensional example. You can have an analogous construction for k-dimensional spaces. The Borel sigma field will be the smallest sigma field that contains all of the open subsets of this k-dimensional space of real numbers. And that Borel sigma field can be denoted b to the power of k, or actually I should just read it as bk. And the set B, that's supposed to be an element of that. So it's a little bit of a technical restriction here on what kind of subsets of this k-dimensional space we can consider. It's pretty analogous to what we had in the one-dimensional case. If you have some reasonable set capital B, it is going to belong to this Borel sigma field, so you don't have to worry about it too much. And then the probability of X belonging to B, so distribution of X applied to B, is going to be the probability measure associated with the pre-image of this set. So the set of all omega such that X belongs to capital B. All right, yeah. Any questions about this definition? So this is going to apply if we have discrete or continuous random variables. And if this is clear, then let's go forward. Then, yeah, if we have discretely distributed random variables, things are relatively straightforward. And we will be able to talk about these joint probability mass functions corresponding to a particular joint distribution. So let me introduce the notation here. Well, yeah, we would like to have some specification of this distribution in the case of discrete random variables. And the notation actually would become pretty cumbersome if I considered many components. So I'm just going to consider two components here, x1 and x2. If you have capital K components, it's actually pretty analogous. But yeah, hopefully you can make that kind of generalization yourself. Then, yeah, we can specify the probabilities of individual values in here if everything is discrete. We will have some value little x1, some value little x2 for the two different components of the vector x. And the p here, that's just going to be some probabilities that you specify. And yeah, we are going to have these values non-zero just for x1 and x2 belonging to some particular set, capital D. So these will be the allowed values of x1, x2. If you like, you can say that this function, this probability mass function, is going to be equal to 0 everywhere else. Actually, I wouldn't want to keep it too abstract at this moment, so I may want to jump back and forth between these formal definitions and some examples. So the example that I have here is actually pretty trivial, but maybe that's going to help with the different definitions. So let's say that we have two phenomena here. We have a roll of a die and we have a coin flip. So in that case, the possible values of the random variables are actually listed here. So these are the possible values of the random variables x1 and x2. And you can think of these pairs as also being outcomes. That is, yeah, if you want, you can think of the set of values of these random variables as being some sample space on its own. But in any case, so if we have one roll of a die, we will have possible values like 1, 2, 3, 4, 5, 6. If we have one coin flip, the values are going to be 0 and 1. So let's say tails is 0, heads is 1. And yeah, these are the possible pairs. Then what would be the probability of each one of these, let's say, of the pair 1, 0? Well, it's going to be 1 over 12. There are 12 possibilities in here. If the die is a fair one, and if the coin is also a fair coin, then each of these pairs has probability 1 over 12. So that's going to be our probability mass function. You would have one number like this for each of the 12 possible pairs that you see here. And yeah, then you can say the probability mass function is going to be 0 for any other numbers, x1 and x2. So that's just to keep the discussion less abstract at this moment. And yeah, the set capital D, that's going to be the 12 possible pairs that we just talked about. Any questions about this at this point? It's probably straightforward. Maybe if something confuses you, it's going to be the notation. So if you have questions about the notation, let me know. Then I may need to introduce some more notation in here. I would like to introduce sets D1 and D2. So D1 is going to be the possible values of x1. D2 is going to be the possible values of x2. And when I say possible value, I mean that this x1 or this x2 shows up at least in one of the pairs, x1 and x2, that belongs to capital D. And a question, what does 4 mean? Let me think. Okay, I'm not sure if I understand which sentence you had in mind in here. Oh, yeah. Okay. It was right here. Yeah, what I wanted to say that there will be some pairs of values, x1 and x2, that have a positive probability. So some combination that can actually happen. And capital D is going to be the set of all of the possible combinations. So for example, for one roll of a die, if you had the pair 7, 0, that's not going to be possible. It's not going to belong to capital D because you cannot get number 7 for the roll of the die. And then, this P, the probability mass function that we specify here, it will be specified only for the possible values, or at least that's what I had in mind when I wrote this. That said, you can definitely extend this definition and say for all of the other values, for all of the combinations of x1 and x2 that are not possible, you simply define this to be equal to 0. So maybe I wrote it in a little bit confusing way, but hopefully this is clear. Thanks for the question. And then, D1 is the possible values of x1, D2 is the possible values of x2. If you have this probability mass function specified, then you can also say what is the joint distribution of x. So here, the probability of x belonging to some set B, which you can also write this way, is going to be some sum of the individual values of the probability mass function. And then, what kind of pairs, x1 and x2, are we going to include in this sum? Well, we are going to include those that belong to capital D, because otherwise the P is going to be 0. And we are, of course, only going to consider an x1 and x2 that belongs to capital B, because here we were supposed to calculate the probability of capital B happening, or capital X belonging to capital B. So we consider this intersection of B and D. We look up all of the possible pairs, x1 and x2, and then we sum the specified probabilities of these values. I guess, do I have something on that? Well, in this simple example, you can, for example, ask what would be the probability that capital X belongs to this particular set. And the set is specified as x1 less or equal to 2 and x2 being greater than 0.5. So what pairs from these possible pairs satisfy that? Well, there are actually just two options in here. You can have 1, 1, and you can have 2, 1. Each of these had probability 1 over 12, so the probability is going to be 2 over 12, or 1/6 in total. Hopefully this is straightforward, but if people have questions, I'm happy to answer. And if this is clear, then let me define some more concepts. We can talk about the marginal probability mass function, or two marginal probability mass functions in this particular case. We can ask for the probability of x1, capital X1, take in some particular value, little x1. And here we would calculate the probability simply by summing up the joint probability mass function over the different values of x2. That is, we are basically ignoring the value of x2, and we are just interested in the probability of x1. So for that reason, we are going to sum up the probabilities over the different values of x2. Or you can say also that you are marginalizing here over this variable x2. Yeah, the interpretation of this marginal probability mass function is simply as the distribution of x1 if you are not interested in the value of x2. And vice versa, you can here compute this marginal probability mass function of x2 if you sum up over possible values of x1. In the case of the roll of a die and a coin flip, yeah, it would be this kind of calculation. So let's say we want to understand the probability that x1 is equal to 3. Then we will be summing the joint probability mass function over possible values of x2. There are two of them, number 1 and number 0. And yeah, we have two terms in the sum. Each of them is going to be 1 over 12. So the total probability is 1 over 6. And of course, this is not surprising at all because we have a fair die and we are just asking for the chance that we obtain number 3 in this particular case. But yeah, I wanted to illustrate this with a very simple example so that all of the notation is clear. Yeah, let me see. I may want to also illustrate this with something slightly more complicated. I have a visualization in here. In this visualization, I'm thinking of having two different random variables. Hopefully it will not confuse you too much because the notation is a bit different. But yeah, I have two random variables, x1 and x2. They are independent, and each of them is drawn from the binomial distribution. It's going to be a binomial distribution that that corresponds to like 10 coin flips. The coin flips can be fair or unfair. Which means that the value of the binomial distributed random variable can be 0, 1, 2, 3, up to 10. So that would be true for variable x1. And the same is also true for the variable x2. I'm going to have two different binomial distributions in here. And the parameter p of the binomial distribution it's going to be P1 for x1 and P2 for x2. But yeah, things are going to be a little bit more complicated in here because what I plotted is actually not the joint distribution of x1 and x2, but instead I plotted here the joint probability mass function of x1, so that's on the vertical axis, and x1 plus x2, that's on the horizontal axis. So really, x1 and x2 are independent, but x1 and the sum, x1 plus x2, they are not going to be independent. So we have some visualization here of the joint probability mass function corresponding to two variables that are not independent. Now, how does this visualization work? For example, yeah, let's say that we set all of these probabilities to 0. There's P1 is 0 and P2 is 0. Then let's increase P1. In that case, yeah, the possible probabilities of x1 are going to shift. And yeah, similarly, the probabilities of the sum are going to shift. x2 is actually going to be identically equal to 0 because I'm still keeping P2 equal to 0. And in this visualization, blue color, light blue color, that indicates a very small value of this joint probability mass function, and like purple color in here that indicates a fairly high value. So the combination of these two variables, x1 versus the sum, that is most likely is actually this one, and this is also quite likely, and other values are less likely. Now, if I decide to also modify P2, then the value of x2 can be non-zero. And the joint probability mass function of these two variables, x1 and the sum, is going to change. And you see it's more spread out in here. Now, the variables are not independent in this case, and you see that if you have a fairly high value of x1, let's say 8, then you are likely to have also fairly high value of the sum. So that could be like 12 in here. I guess I didn't say explicitly what these individual squares mean, but yeah, this square in here is the probability of 0, 0. This square here, or its color, represents the probability of x1 being equal to 0 and the sum equal to 1, and so on and so on. So yeah, at this moment it looks like the highest probability would be for x1 equal to 5 and the sum equal to 9. So that's the meaning of this picture. But yeah, please tell me if you have any questions about the visualization. I want to say more about it in a second. And yeah, I wanted to use this particular visualization to just say what the marginalization corresponds to. So if someone asks you, based on this picture, assuming that you know all of the values in these individual cells of the grid, if someone asks you what is the probability that x1 has the value of 8, then you would take these cells that you see here and you would sum the individual probabilities. That corresponds to the marginalization. If someone asks you what is the probability of this sum x1 and x2 being equal to 9, for example, you would take this column and you would sum up the individual probabilities. And you would get a distribution of just one discrete random variable, x1 plus x2. That is, yeah, the marginalization here corresponds to summing the individual rows or summing the individual columns. Any questions about this? I guess it's relatively straightforward, but if there's any confusion, I'm happy to clarify. And if there is no confusion, let's go forward. I have also some discussion of conditional probabilities in here. So you can ask, for example, given that the sum in here is equal to a specific value, let's say 11, so that would correspond to this particular column. So given this, someone would ask you for the probability of x1. So in that case, you would work with the probabilities in this particular column. If you sum them up, then they are not going to be equal to 1, right? But what you can do with these probabilities is to renormalize them. You can take the individual entries in this column and then divide them by the total probability of being in this particular column. So that's the answer to the question, what's the probability mass function of x1 conditional on x1 plus x2 having a specific value. I think I will have to elaborate on it a little bit more, but yeah, the formula that will be right here. I will provide also some simpler example to fix ideas. If you want to define this conditional probability, or define the conditional probability mass function of x1 given x2, then you will take the joint probability of x1 and x2, and you would divide it by the marginal probability of x2. I think one of these examples that I have here will provide some more motivation for this formula. Yeah, once you compute this ratio, you can say that this is the probability mass function of x1 given this particular value of x2. Okay, no questions. So let me say that this is relatively straightforward here, but it's going to be very, very subtle when we switch to continuous distribution. So that will be something to discuss the next time. And I'm not sure how fast I will be able to go here, but I have a very simple example that's almost trivial, an example with rain and lightning. And hopefully I will be also able to say something about the Bayes theorem, which is very fundamental. Yeah, hopefully I will also cover some intuition related to that. So what's this example? It's supposed to be super simple with some numbers that I just came up with. And here we will be considering the weather at a particular location at a particular time. We are going to have two random variables in here. x1 is going to be the indicator random variable for rain. And x2 is going to be the indicator variable for lightning. A1 is an event of rain. A2 is the event for lightning. And if, for example, you want to think about rain and lightning happening both, then it would correspond to this particular intersection of A1 and A2. Then what would be the probabilities in this example? I just came up with these numbers. Let's say that you have a 10% chance of having rain and lightning, so some thunderstorm. You will have a 20% chance of rain and no lightning. It's quite rare to see lightning without the rain, so maybe just 1% probability in there. And no rain, no lightning, that will be 69% probability. Yeah, let's take these values as given. What would be the joint probability mass function? We can organize it into this kind of table. So, for example, this one, P00, that's the probability of no rain, no lightning. It's this 0.69. Then, what about the marginal probability mass functions? Here we need to perform some summation. If you want to know the chance that there is no rain, we are going to sum these joint probability mass function. We are going to sum the joint probability mass function over different values of the lightning indicator variable, and we get 0.7 as a result. So hopefully I don't need to go through these individual values. You get different probability of no rain, probability of rain, probability of no lightning, probability of lightning. And as for conditional distributions, you can ask what is the conditional probability of a lightning given rain? It would correspond to this kind of expression, and our prescription there was we take the joint probability mass function, evaluate it at these values, so it's going to be 0.1 in this particular case, and we divide by the marginal distribution, evaluated at the presence of the rain. So this is going to be 0.2 plus 0.1. Overall, we get 1/3. So there's a 1/3 chance that if you see rain, then you will also see lightning. Now, I want to argue that this is actually pretty intuitive. So if you have some very large data set and the proportion of the different possibilities, if the proportions are actually given by these four numbers, then for sure, if you are trying to understand what's the chance of a lightning, if you see rain, only the second row in here is relevant. So if 20% of your observations correspond to a rain without lightning and 10% correspond to the probability of rain and lightning, then yeah, it's kind of natural to understand that the probability of the lightning given rain is actually 1/3. So yeah, in 30% of the samples you see rain. Only in 10% of the samples you see rain and lightning. So yeah, the probability is going to be 1/3. That's kind of the intuitive motivation behind the formula that I just wrote down for the conditional distributions of these discrete random variables. So that's one circumstance. You can also ask a similar question. What's the chance of rain given lightning? And the calculation is actually very analogous. You would be focusing then on this particular column, and the chance of rain given lightning in the end is 10/11. So that's some illustration with a very simple example of these concepts. And I have a little bit more to say about that. Hopefully I will be able to connect it to the Bayes theorem. But do people have questions about this? It's very easy at this moment, but yeah, let me say again that when we get to continuous distributions, it's going to be fairly non-trivial. All right, then I would like to get here also to the Bayes theorem. Unfortunately, I don't have that much time, but I will try to be quick in this discussion, and we can definitely talk about the intuition in more detail the next time. Well, first of all, I want to say that the Bayes theorem, the very famous Bayes theorem, is an identity like this. It tells you the conditional probability of some event A1 given A2 if you know the conditional probability of A2 given A1, and if you also know these other terms. So this is where we want to get, and I'm hoping to provide a very quick derivation of the Bayes rule, and then we can talk about the interpretation and intuition. This is a slightly different version of the conditional distribution formula that I had before. Here, I'm writing things in terms of events. So we are going to think about event A1 and event A2. And we may want to ask, what is the chance of A1 given that event A2 happens? Then it's going to be a ratio. By definition, it's going to be a ratio. It's going to be the probability that both A1 and A2 happen. And we are dividing here by the probability that A2 happens. So it's a little bit different notation from what we had before, but hopefully you recognize here the numerator as some joint probability mass function of the corresponding indicator variables. And hopefully in the denominator, you recognize the marginal probability mass function of the corresponding indicator variable. So that's something that we take as given. And I should warn you here, you should not condition on events that have zero probability. So in that case, we are just not going to define this. I will definitely elaborate on this the next time when we discuss continuous distributions. But now let's focus on just these two events, A1 and A2. Let's assume that this probability is non-zero, so that all of our expressions make sense. Then let's take this definition and let's rewrite it. We can multiply by the denominator to obtain an identity like this. And of course, we will have a similar definition also for the role of A1 and A2 swapped. So we will have this kind of identity. That is, the probability of this particular intersection is the probability of A1 times the conditional probability of A2 given A1. So these two equations basically just follow from our definition of conditional probability. And then we make a very simple observation, which is that an intersection of A1 and A2 is the same thing as the intersection of A2 and A1. That is, at the left-hand sides of these two equations, they are equal to each other, which implies that the right-hand sides must also equal to each other. And we get this formula right here. So we are almost there. And all we need to do at this moment is just to take both sides of this equation and divide them by the probability of A2. Again, assuming that the probability of A2 is non-zero, and we get this formula right here. So this is a super famous theorem, the Bayes theorem. And I think we will need to talk about it in a little bit more detail. But I may want to try to provide some very quick discussion at this moment. Yeah, let me connect this particular formula that you see here also to the previous example with the rain and the lightning. And as for intuition, let's have some more detailed discussion of the intuition behind the Bayes theorem the next time, because today, yeah, we don't have that much time remaining. So I think I will have to also introduce some more terminology in here. You can say that this probability of A1, maybe I can move this a bit. Yeah, the probability of A1 that shows up in here, yeah, you can call it the prior probability. So before you make an observation of A2, this is the probabilities that you would assign to A1. And you can also use the term posterior probability for this kind of conditional distribution. So if someone tells you, for example, that A2 happened, what is the probability according to you that A1 is going to happen? So that's the left-hand side of the Bayes theorem formula. And according to the Bayes theorem, it must be equal to this ratio. And I rewrote the exact same ratio here in a slightly different form, kind of emphasizing that there is this factor of the probability of A1. You see that the prior probability and the posterior probability, they differ by this particular ratio. Yeah, you can call this an update factor, although this is not any common terminology. I just made up this term, update factor. So if this update factor is pretty much equal to 1, then knowing that A1 happened tells you almost nothing about the probability of A2. But if this update factor is either very large or very small, then you will shift your beliefs about the probability of A1 if you have observed A2. So something we should definitely discuss in more detail with intuition the next time. But today, probably the last thing that I will be able to accomplish is just to show you a calculation associated with this, also associated with the example that we had with the rain and lightning. So what we calculated earlier today was this. That is, we had the probability of lightning given rain being 1/3. We had the probability of a rain given lightning 10/11. And yeah, I just want to point out in here that if you wanted to calculate, again, the probability of rain given lightning, then you could also use the Bayes theorem. You could use the formula that we just derived. So the Bayes theorem, also called Bayes rule, will tell you that this conditional probability is equal to this particular ratio. We want to zoom this a bit more. And yeah, this one is the probability. This one is the probability of lightning given rain. We computed that it's 1/3, right? So we have 1/3 in here. Here we have the probability of rain. So that's going to be this 30% in here. And we need to divide here by the probability of lightning, which was 11%. So if you do the math, then you will be able to convince yourself that this is actually equal to 10/11, which agrees with what we computed previously. That is, yeah, in this particular case, the Bayes theorem gives you some identity that you could potentially use to evaluate this conditional probability. If someone gives you the opposite conditional probability. I think I have a lot more to say regarding the intuition related to the Bayes theorem. Unfortunately, we will have to leave it for the next time. But if people have any questions at this moment, I'm definitely happy to answer. Yeah, was it all clear what we discussed? I guess it's a relatively straightforward matter. It should get more complicated next time. And yeah, so what remains for the next time? We should talk in more detail about the intuition behind the Bayes theorem and how you apply the Bayes theorem to the case of something that you are interested in, some phenomenon that you want to study, and corresponding data evidence. We should for sure talk about conditional distributions for continuous variables. It's very non-trivial. We will see a paradox related to that. And yeah, we should also talk about a relatively simple things, simple concepts like covariance and correlation and so on. So actually a lot remains for the next meeting. But hopefully you will be able to make it, and hopefully I will be able to make the discussion brief enough the next time.